Now consider propene molecule CH2 double bond CH single bond CH3. When propene is reacted with the chlorine at a very high temperature, that is 500 degrees Celsius, instead of addition reaction, we get substitution reaction where one H atom of the CH3 is replaced by a chlorine. So we get CH2Cl. Then this reaction happens by a free radical mechanism. Initially, the Cl-Cl bond undergoes homolysis to give two chlorine free radicals. Then one chlorine free radical will react with the propene molecule, and the methyl group with the ACH bond will undergo homolysis so that H radical is freed, and this H radical combines with the Cl radical producing HCl, and then a radical center is created over this carbon. That means an unpaired orbital is created over this carbon. Now that radical CH2 double bond CH CH2 with a single electron on CH2 is called an allyl radical. Then an allyl radical can undergo resonance. Now here this pi electron pair shifts in this direction, and this half-headed arrow shows that there is only one pi electron moving in this direction, and the other pi electron will be remaining over this carbon as a free radical center. Then the single electron formed over this carbon in an orbital which is parallel to the orbital over this carbon containing this single electron will overlap to form a pi bond, so that there is movement of pi electron pair along the chain. So there is resonance, stabilization of the radical, and that radical is called allyl radical. Now allyl radical can further react with a chlorine molecule. Now we can take any one of these canonical structures. We are taking this one, CH2 double bond CH, single bond CH2 with radical center. Then a radical reacting with a molecule, then Cl-Cl bond undergoes homolysis, and H radical is created, and a Cl radical is created, which will combine with this radical center to form a sigma bond. Now this free Cl radical here will combine further with a propene molecule, and the reaction goes on. It is called a chain reaction. Now here this CH2 group is called allylic position, and the compound formed is called allyl chloride. So allyl group is CH2 double bond CH single bond CH2. That group is called allyl group. Now here this molecule is called cyclohexene. It contains a double bond. Now here the CH double bond CH single bond CH2 system, this system is similar to an allyl system, and here this CH2 forms the allylic position. Now we can consider another allylic system like this, CH double bond CH single bond CH2, another allylic system. Then consider a mirror plane, a mirror passing through this plane, so that this CH2 and this CH2 are related as object and image groups. Hence we can say these two CH2 groups are similar. So when bromine reacts with this molecule, this type of mechanism occurs. Br bond first undergoes homolysis to produce Br radical. Then this CH bond here undergoes homolysis, producing a radical center, and H radical created here will combine with Br radical producing HBr, and this radical created here will react with another Br2 molecule producing this product. So this is called allylic chlorination or allylic bromination. Now Next, we can consider the forces of attraction operating between alkyl halide molecules. Now, first of all, we shall see what is London dispersion attractive forces. For any atom or molecule, the center of electron clouds and the center of positive charge coincides. The same point represents the center of the electron cloud and the center of positive charge of the nucleus. Now, as the electron is moving around the nucleus, sometimes it may happen that instantaneously or momentarily the center of electron clouds and the center of positive charge are slightly displaced. So, the center of electron cloud slightly moves away from the center of positive charge of the nucleus. Then, at the center of positive charge of the nucleus, at that side, a delta positive charge is created, and on the opposite side, we get a delta negative charge. And as the electron cloud center is displaced, the electron cloud also shows a slight distortion from the spherical shape. So, such displacement causing the production of a dipole is called instantaneous dipole. Now, such a dipole can induce dipole into another molecule or atom coming near it. Now, what happens is that the first dipole with its negative end will repel the electron cloud of the second molecule or atom. Now, then a dipole is created in the second molecule due to the repulsion of the electron cloud. So, electron cloud will be moving away from this region and they will form a shape nearly like this. So that this end will be having a delta negative charge and this end will be having a delta positive charge. Now, this is called induction. So, the first instantaneous dipole induces a dipole in the second molecule or atom. Then the opposite charges can attract, and such forces of attraction, attractive forces, are called London dispersion forces or instantaneous dipole induced dipole forces. Now, all atoms and molecules will possess London dispersion forces. Now, consider a large atom which is nearly spherical in shape. Then the nucleus and the valency electrons of a large atom are at a longer distance apart, so that the nucleus will be having a lesser attraction over the valency electrons of a large atom. Now, the valency electrons occupy the boundary of the electron clouds. Now, a large atom will be having a large surface area also, so that a large extent of distortion can occur, a large dipole can occur, so that the induced dipole will be large and the instantaneous dipole will be large, and consequently the forces of attraction will be large. So, a large surface area means large forces of attraction. So, London dispersion forces depend on the surface area of the molecule. As surface area increases, the extent of attraction also increases. As molecular weight increases, the size of the molecule increases and also the surface area increases, and hence the London dispersion forces also increases, and such forces are collectively called van der Waals forces, And van der Waals forces include not only London dispersion force but dipole forces, dipole induced dipole forces, etc. Now, higher the molecular mass of a molecule, higher is the surface area of the molecule, and higher is the extent of van der Waals forces operating between the molecules. Now, in hydrocarbons, the only force operating between molecules is London dispersion forces, and greater the surface area of the molecule, higher will be the extent of attraction between the molecules. And as molecules attract, the substance turns from gaseous to liquid to solid. Usually, hydrocarbons with low molecular mass are gases. Up to butane, they are gases. Then coming to pentane and other members, the tendency towards liquid increases, and heavier hydrocarbons are solid. So as molecular mass increases, surface area increases, extent of attraction van der Waals forces increases, and they tend towards the liquid to solid state. Now, for a given volume, a sphere is having the least surface area. That is a mathematical observation. Suppose a cube and a sphere are having the same volume, then surface area of the cube will be higher than that of the sphere. So we say for a given volume, surface area is minimum for a sphere. Now, in the case of hydrocarbons, the only force operating is London dispersion forces, and they depend on the surface area. Now, when we come to branched hydrocarbons in which there are branches, alkyl group branches in the molecule, then such molecules will try to assume a coiled conformation. And this coiled conformation is nearly spherical, and since a spherical molecule, a spherical shape is having minimum surface area, the extent of van der Waals forces or London dispersion forces will be less. So during branching or in a branched hydrocarbon, the London dispersion forces are less because of the lower surface area. So a normal compound means a straight chain compound like N-pentane and a branched compound like neopentane. The surface area will be lesser for neopentane because it is almost spherical. When isopentane is considered, it is nearly spherical but not so much spherical as neopentane. Then the tendency towards liquid decreases, the force of attraction between molecules decreases as the molecule is getting towards a spherical shape, so that the liquid state is attained by normal compounds than by branched compounds. Or even if they acquire liquid state, the boiling points will be lesser for a branched compound than a normal compound. So normal pentane is having a boiling point of 36 degrees Celsius. Isopentane is a branched compound, so try to assume a coiled conformation and assumes a near spherical shape, and the boiling point is decreased to 28 degrees Celsius. And neopentane, which is more spherical in character with the least London dispersion forces, that is attractive forces between molecules, so that the boiling point is 9.5 degrees Celsius. Now, alkyl halide molecules are polar because the electronegativity difference between carbon and halogen. See, CH3Cl will be having a delta positive carbon and delta negative chlorine. So such molecules are called polar molecules. Now the force operating between alkyl halide molecules is dipole forces. So this dipole will attract another dipole. So there is weak attraction between the Cl of one molecule and the CH3 of another molecule. Now that is the main force of attraction between alkyl halide molecules. And again, all molecules possess London dispersion forces in common. So these two forces of attraction are operating between alkyl halide molecules. Now boiling point of alkyl halide molecules are higher than the corresponding hydrocarbons having similar or same molecular mass. Suppose a hydrocarbon is having the same mass as that of an alkyl halide, then the alkyl halide will be having a higher boiling point than the hydrocarbon if both are liquids. And this is because dipole forces are stronger than London dispersion forces. So hydrocarbons have only London dispersion forces among the molecules, and if two molecules, that is one alkyl halide and another hydrocarbon, have equal molecular mass or nearly equal molecular mass, then the alkyl halide will be having a higher boiling point than the hydrocarbon having same or nearly same molecular mass, because in alkyl halide the force of attraction is dipole attraction, which is stronger than London forces of attraction operating between the hydrocarbon molecules. Then for the same alkyl group, the boiling point of alkyl halides vary as alkyl iodides greater than alkyl bromide, greater than alkyl chloride, greater than alkyl fluoride. Now if you consider the dipole forces operating between molecules, then the largest dipole moment will be provided by alkyl fluoride, because the electronegativity difference between carbon and fluorine, carbon with electronegativity 2.5 and fluorine with the electronegativity 4 is largest than alkyl iodide, where the electronegativity of carbon is 2.5 and that of iodine is 2.7. So RF is having a greater dipole moment than alkyl fluoride, so that the fluorine atom in alkyl fluoride is having a larger extent of partial negative charge than the partial negative charge over iodine in alkyl iodide. Now if that is the case, then the force of attraction between two RF molecules should be larger than the force of attraction between two Ri molecules, because the RF molecule has got a large dipole moment and a large fraction of negative charge over fluorine and a large fraction of positive charge over carbon. But the thing is that alkyl iodide, in which iodine is a large atom, has a large surface area, and hence large van der Waals forces, especially London dispersion forces, operating between alkyl iodide molecules. And again, there is one more reason. See, consider two alkyl iodide molecules, CH3I and CH3I. Here there is delta positive charge over carbon and delta negative charge over iodine. Delta negative charge over iodine and delta positive charge over carbon. Now this delta positive carbon will be distorting the electron cloud of iodide towards itself. And since iodine is a large atom, the distance between the valency electron of iodine and the nucleus will be large, and so the attraction of the nucleus over the valency electron will be less, so that the electron cloud of iodine group can be easily distorted towards itself by the partially positive carbon. And this yielding power of iodine towards the attraction of positive carbon is called polarizability. And we have seen this polarizability in a previous video. So iodine is highly polarizable. That means there is a greater extent of electron pair movement between iodine of one molecule and methyl of another molecule, so that the force of bonding, attraction forces, are greater, and the polarizability of halides decreases from iodide to bromide to chloride to fluoride. So the high polarizability of iodine group may be one of the reasons why alkyl iodides are highly associated and their boiling points are very high. Now, about the solubility of alkyl halides. Now, for a molecule as a solute to be soluble in a solvent, suppose the solute is represented by A, and here alkyl halide is the solute, and suppose B represent the solvent. For example, say water. There are three types of attractions or interactions. Interaction means here attraction. Here it means attraction. Between solute and solute, that is called AA interaction. Between solvent and solvent, that is called BB interaction or attraction. Between solute and solvent, that is called AB interaction. Now, if AB interaction is greater than AA interaction or BB interaction, so if AB interaction, that is interaction between solute and solvent, is greater than the interaction between two solute molecules or two solvent molecules, then the substance will dissolve in the medium. Now, if we take water as a solvent and alkyl halide as a solute, between solutes we have dipole attraction. So this is a attraction. That is, between alkyl halide molecules we have dipole attraction. Now, BB attraction between water molecules, the strongest force among the weaker forces, that is hydrogen bonding. So hydrogen bonding is stronger than van der Waals forces, that is dipole forces. Then what about AB interaction? See, alkyl halides cannot form hydrogen bond with water. So water is a dipole and alkyl halide is a dipole. So the AB interaction here will be dipole attraction. So that AB interaction is less than BB interaction. That means the substance will not form strong bonds with the solute, that is alkyl halide, will not form strong bonds with the water molecule. And water molecules form strong bonds among themselves, and that is called hydrogen bond. And hydrogen bond is having a higher energy than dipole forces or van der Waals forces in general. And so the alkyl halides do not dissolve, alkyl halides do not dissolve in a water medium. So alkyl halides are insoluble in water medium. That is all. Thank you.